Ouais, c'est pas ici. C'est bon?
Yeah, I don't know.
We're going to start in 1 minute.
The Wi-Fi is not. Sure.
Or if not, just put the.
Yeah, but this is what's going on here.
Don't worry, we have time.
Okay, yeah.
Because the lecture after
Yeah.
is between us.
Okay.
If we have any delays.
Okay.
No problem.
Doesn't want to work. Otherwise, we can maybe. I don't know if there's an HDMI cable. But then.
Can you send by mail?
Yeah. In our conversation, right? Let me actually search internet with my phone. Maybe it's better. I think the PowerPoint is in OneDrive,
Yeah,
and then I need the
I think
internet.
it's better if you can connect for the Wi-Fi and share from the laptop.
Yeah,
Yeah.
but this Wi-Fi is very slow. Like I cannot even. Maybe there's a better one or. No, it works. Okay, so I join my screen.
Okay, so yes, please join.
Where? This one?
This one, yeah.
Okay.
Please accept.
Okay, I join.
Share the screen, share. Then you can turn it up.
There's no restriction for the.
Yeah.
Hey, yeah. Finally. Okay, I'm gonna.
So hello everybody. The online participant. Can you hear me, the online participant?
Can they hear you?
Hello. Please say something. Yes. Okay. So okay. Thank you for being here, all of you. So for beginning the opening sections, I would like to introduce Guillermo Munoz. Sorry.
It's okay.
So thank you for being here. So he is a master student in quantum engineering at ETH Zurich, and currently an intern focused on quantum error correction and qubit CAD architectures at Alice and Bob, right?
Yes.
And his internship work on concentrates on simulation and design aspects, and that support the fault-tolerant CAD qubit system. That is an area essential to Alice and Bob's approach to scalable quantum computing. And today is going to talk about quantum error correction with CAD qubit. Please.
Thank you very much. Does this work? Yeah, I think this is mouse. Maybe I have to plug it in.
Yeah. We tried this morning, but it doesn't work very well.
No worries. Then I can use the Mac otherwise. Thank you. So welcome everybody. I'm very excited to give this talk. As I said, I'm quite fresh into this field of quantum error correction, but it's a pleasure for me to give you a brief introduction. I don't know if anyone here is familiar with quantum error correction or if it's the first time you hear about it. I mean, it's okay. Just is it the first time for everyone? No?
We hear about the title.
Yeah, okay. Yeah, you hear it in the title. So this introduction has as a main objective introduce you to the basics so that you get the feeling for it. Why is it important? Why do we need it? Why is everyone talking about it? So first of all, let me introduce myself, if this wants to work. So I have my background is in engineering physics. I did my bachelor's in Madrid, Spain. Then I moved to Switzerland where I started my master's in quantum engineering. And right now I moved to Paris to do an internship of quantum error correction at Alice & Bob. So for those of you who don't know about the company Alice & Bob, I'm gonna briefly say a couple of words. We are quantum chip designers, and we are based on a superconducting circuits platform. This means that we use cryostats. We fabricate and design chips that we place in these huge fridges. So they are close to 0 Kelvin temperatures where they exhibit quantum properties, which we think they are very cool, that can be used for many applications, as I will say afterwards. And to show you a few pictures of what we do, here's an example of a chip we fabricate. And if we have a closer look at it, at the end of the day, this is a silicon substrate on which we place some metal with close temperatures to 0 Kelvin exhibits superconducting properties. And by engineering circuits on top of this metal, one can actually see and play with quantum mechanics at the end of the day. I'm not gonna get into the details of the chip or anything about hardware because this introduction has some other topics, but also to introduce Alice and Bob a little bit about the numbers. The company was founded in 2020 by Theo and Rafael. They are both the co-founders of the company, and they were doing their PhDs in superconducting circuits when they realized in one of their papers that in which they actually fabricated one of the first CAD qubits that they wanted to bring this technology to industry. And so it started in 2020. Now we are more than 140 people. There's two offices in Paris and Boston, and around more than 130 million raised to date. So the company is growing fast. And yes, we are in the race for building the fault-tolerant quantum computer. So first of all, a brief introduction to quantum error correction. Why do we need it? Why is it important? I think this whole day also you've been talking about quantum error mitigation. So how are these all concepts related? So first of all, quantum computers expand the set of problems we can solve, unlocking a technological revolution. I think some of you may be aware of this. That's why we're here today. We're very excited though about this. So let's put the most famous, most trendy example of all time. This is the encryption, RSA encryption, so what it takes to factor a number. So let's put three examples. We're gonna try to decrypt a bit or a key with 512 bits, then twice as that, 1024, and then 2048. So for a regular computer, this is a classical laptop. Our laptop here, it will take 0.5 milliseconds to just decrypt a bit with 512 bits, a key with 512 bits, but it will already take 3 months to take double as that, and it will take 6 trillion years to just do double as that. So this is for you to get a feeling of what this scaling in magnitude of the problem looks like for like the time really explodes. Like that's why it's a safe encryption nowadays, and that's why we use it, because it takes 400 times the age of the universe to actually decrypt it. But what about for a quantum computer? This goes in another scaling. So we would take 10 hours 1 day and 1 week for each of the problems. Now, as you can see, the scaling is much more linear, and we're beating the exponential scale up. So this is not only for RSA encryption, this is for many other applications. I mean, there's applications in life sciences, chemicals, energy, telecommunications, manufacturing, logistics, finance, you name it. And actually some consulting groups have started to estimate how much value this will open in the future. And this number over here, $850 billion, is what the Boston Consulting Group estimated that this could open, because there's this problem, but there's many other problems that could benefit from a quantum computer in many fields. But what's the problem? Why don't we have a quantum computer today? So they are not reliable, they are very faulty, and that's actually the problem. We need very low error rates. We need something that is almost close to perfect to actually get something out of it. And to also illustrate with some numbers how we're doing on this problem, I'm going to put a line here where I'm going to show the error probabilities in a logarithmic scale. So this is where we are today. This is, for example, an error rate of 10 to the minus 2. This is more or less a 1% error every calculation you do. And this is today. Now, the future hardware speculation says that we are going to achieve this level of error probabilities. But you can imagine that getting here today took us 15 years already, just to get here, to have qubits and everything. And you can imagine that to get to that parameter is going to take some more years. But the actual surprising thing is that our applications, they live right here. So we need really 10 to the minus 14, 10 to the minus 15 in our error rates so that we can actually do something useful. So what's going to bring this gap to bring some qubits that are really faulty to almost perfect? It seems like a huge gap, and we think there's only one way around it, or we have found out there is only one way around it, and this is to actually correct errors. So I think up to here you've been talking about error mitigation, and would be this part over here in which we actually realize we have noise, we have faults, we have errors, but we are going to try to do something around it to get something useful out of it. But in fault tolerance and error correction, what we say is no, we're going to actually do something against the errors. Let's correct them and let's actively do something. And when we get to this part, this would actually be the perfect ideal quantum computer that you can put any application, any problem, and you can run anything. So this is actually what it's called the NISQ era for noisy quantum computers that you actually can do stuff with. And this is the fault tolerant quantum computing. Fault tolerant means that there's faults inside of our chip, there's errors happening all the time, but we are tolerating them, we are correcting them. So our solutions are actually there and we can calculate them. So let's put some numbers here also for you to get some feeling for it in problems in chemistry, finance, and cryptography. So how many perfect qubits we would need for a chemistry, finance, and crypto problem? I don't know if you, for example, how many qubits do you think it would need to run I don't know, some chemistry problem, more or less? Do you know any order of magnitudes? Is it 20? Okay.
10,000.
Yes, exactly. It's more than 20. It's like around 100, 1,000, even 10,000. So we really need, and I'm talking about perfect. This is really ideal things that come from textbooks, like 1,000, 10,000. And number of gates. Yeah.
When you mean perfect, it means logical qubit.
Exactly, okay. Exactly, logical qubit. I will get to that concept in a second. So the number of gates here is enormous, like 10 to the 14, 10 to the 10. So you can imagine that if we make just a slight error on each one, at the end of all the circuit, this is going to be a mess. So we really need something very perfect. So error per gate, you can see that it's 10 to the minus 17, minus 13, minus 14. So you get the game. Now, classical bits, they just have zeros and ones. They are super nice because almost they never flip. Like it's really weird to have a transistor in your computer that suddenly flips and goes from 0 to 1, because that never happens actually, because of how the transistors are built. This is super safe. Like transistors live in the 10 to the minus 17 error regime, in which we can completely neglect that nothing's happening there. However, a qubit is much more than just a 0 or a 1. They live in the surface of the Bloch sphere, as you all know, and we can have any arbitrary superposition between the 0 and the 1. And we can actually have more than that. We can have phase information. That's actually what makes qubits so special and what makes them do these calculations and to solve these problems. Now, that's the good part, but the bad part is that we have more problems. So we not only have bit flips, which means it goes from 0 to 1 when this qubit has some interference going on or some noise going on. We also have phase flips that would actually destroy our phase information. And you can imagine any error could be a combination of these two. And what we end up with is losing our information, and our qubit is dead in super short timescales. So we can do nothing with it. So this talk is about redundancy. So redundant error correction is the best solution today to escape this paradox. What we will do in quantum error correction in very simple words. And to put it in 3 sentences, in the first place, we're going to have the same information within a set of qubits. Second, we're going to check if the qubits in a set agree with each other. And third, if they don't agree with each other, we're going to have to correct some of them. So instead of having just one block sphere encoding one qubit, we're going to have multiple of them. They are all going to be having the same information. And if one of them goes with an error, we're going to compare the rest, and we're going to spot that error and correct it. That's the whole game of quantum error. So this is not an idea that it was only for quantum. Like, this comes from a long time ago. It's called classical error correction. It's called coding theory, and it uses the redundancy to correct for errors. And the example, the most known example, is the repetition code. So let's say we have Bob and Alice. This is not about the company, but it's just two examples of two people, Bob and Alice. They're trying to communicate, and they want to send a 0 or a 1 through a channel, okay? And Bob asks how Alice is doing, and Alice sends a 0 or a 1, but with some probability, let's say 10% probability, it's going to flip because of an error happened. Now, if Alice sends something and Bob receives 0, what's the probability that Bob's information is the wrong one? Actually, here it's just 10%. Here it's just 10%. But how can Alice do better than this and tell information that is more reliable? I don't think am I in the middle of the screen, maybe?
It's a good idea, yeah.
Is it good for everyone there? Yeah. So Alice response X sends 000 for 0 and 111 for 1. What this makes is that if there's only one error at a time, this is a huge assumption, but let's take it for now. Bob received this information, and now he knows an error happened, and the original information was just a 0. And now the risk of failure is much lower because Bob can now actually detect and correct the corrupted information. And this is the whole game still. Like, the more you copy and paste the same information and you increase your redundancy, the stronger this message is going to be against noise. So if we put 5 zeros instead of just 3, this is the failure risk. I mean, you can actually compute this probability. It's really easy. And the more you increase this, the more strong you're going to be against noise. So this is what we call exponential suppression of errors in the code distance. I'm going to talk about what is the code distance, but you can get the feeling for what an exponential suppression of errors looks like. So can we do the same in quantum is the question we raise here. And so now the question would be not just how is Alice and how is Bob. It's more like a quantum question, like how is the Schrodinger cat doing? What is your superposition? Blah, blah, blah. So Alice sends some other kind of information. This is a quantum state with some superposition. And actually, our information is stored in these alpha and beta coefficients. That's what makes our qubit a qubit, is that we can have arbitrary superpositions. And Bob, he receives the original information, or the one with a flip in the bits with a 10% chances. Let's say that's more or less what the analogy in quantum would be. And now the error correction strategy, as you can see, it's more or less the same. We're going to put or encode our qubit in some larger superposition with more qubits, with more states. And this we're going to call our logical qubit. This just has one information of one qubit, but it's more robust against the noise. Now, Bob is going to receive this state, and is going to wish to correct the state. Now, this might be not the first thing you would come with, because you would say, okay, I take this and I copy it 3 times. However, we know because of the no cloning theorem that we cannot do this. So that's why it looks like a super kind of special superposition. It's not just copying and pasting this state 3 times. This would be the correct analogy. So what Bob receives can be 4 things, assuming again that we only have one error at a time. He could receive one of these 4 possibilities of no error, error on the 3rd qubit, the 2nd, or the 1st one. Now, I want you to think about how can Bob actually know that an error happened? And why is this not so trivial information? It's because, as we know, we don't want to actually measure our qubits. We want them to have this information to then do stuff with it. So it's it's more subtle. So there's different rules of the game. I mean, you can ask several questions. They can be just no, but they don't have to. They cannot collapse your quantum information. But it's not as simple. It's not just okay. I'll measure my qubits, and if they agree, no, because we don't want to collapse the state. So what's a very bad question is the first qubit in 0? Then you would collapse your states to any of these 8 options. You would see, oh, okay, that maybe these 2 guys don't agree and I had a 0, but this is just bits of classical information. You destroyed your superposition and you're lost. So projection from the measurement is both a curse and a blessing. So we have to treat it with a little bit of careful. We have to be careful about it. So what we're going to ask is a different question. This question is going to be more subtle. And bear with me, we're going to assume you can do this question without any measurement and without any measurement of the logical qubit. We're going to be asking, are the first 2 qubits in the same state? For the moment, assume that you can do this question without any measurement. If it's a yes, this would split your 4 options into 2. If it's a no, it would be the other 2 remaining options. And in the same way, you can ask, are the 2 last qubits in the same state? This would again split your options, and at the end of the day, you have more or less a tree mapping your questions and answers to the error that happened. Like you can build such a table that says, if I have 2 yeses, then there's no error. You have a yes and a no, there's an error on my qubit number 3. If it's a no, and you get the rest. So we managed in this way to locate the error without perturbing alpha and beta. And this is really cool because if I have this information of an error happened on my 3rd qubit, then I can apply the X gate on the 3rd qubit, and then I fix the error and I have my super nice information, my super nice superposition. Okay. So to sum up a little bit this first part, we don't want to directly measure our qubits. It destroys our quantum information. And instead, we want to use indirect syndrome measurements. These questions that I was talking about, we call them syndromes and syndrome measurement. And we are going to ask some more subtle questions to our qubits. Let's say qubits don't like very straight questions to them. You have to more or less surround them. And with this approach, we're going to locate the errors and be able to correct for them. So now let's go to the next layer of form. Let's say to present it more formally with a very simple example. I want you to think about quantum error correction as anyone in the classical world would think about sending some information. So you have some message that you first encode according to some rules that we call the code. This is going to be sent through some channel, which I here represented with 3 lines for so that you'd imagine the quantum circuit. And then the receiver is going to decode that, and it's going to get a message out. Now, the problem is that in this channel, there's noise, and something's going to happen to our state, and we want to fully get what we started with. So let's say we only have bit flip errors, and this means X gates. And so the message was the superposition. We have encoded it. So we are in this step. We have this. We want to send this to Bob. And for you to think about how this would look like in a quantum circuit, here we send, for example, the alpha 0 plus beta 1. We do some 2 C0 gates, so just 2 states initialized in 0. And what we get out is exactly this. I'm not going to prove it. Maybe just you see it immediately. That's super nice. It's not so obvious, but believe me in this, that just with 2 C0 gates and 2 extra qubits, you have your encoding. Really easy, very easy. And so how are we going to do these questions of asking, is it the first and the second? Do they are in the same state and everything like this? We're going to have to add another qubit that is just going to be there to help you answer these questions. We call this qubit the ancilla or the auxiliary qubit. So these guys are from here. They store our data. They have our information. And this guy is just there as a help to be able to answer the question. So when we put 2 C0 gates connected to this auxiliary qubit, and we measure this one, this measurement being a 0 or a 1, it's going to tell us if they are in the same state or if they are different. To put an example, no matter what this state was in, if there was an X error here, this is going to propagate through our target and through our control, and the target is going to flip. And this is going to also flip our measurement in the set basis. So there you could see that a single error happened. Is this clear? Can you see it more or less? So then, when you realize that an error happened, what you do is you apply the corrections from the syndromes. Syndromes is another concept from this field that means the information that you are getting out of your logical qubits that is going to help you correct those errors. So this information that came here, like this flag saying, oh, an error happened, that's your syndrome. And then to get back your quantum information, you apply the X gate. So similarly, for phase flip errors, now one has to encode your information in a different way. And this is, instead of in the 0, 0, 0 plus 1, 1, this would be 3 pluses and 3 minuses. So here we don't have bit flip errors, we just have phase flip errors. So the game here is we're gonna put our redundancy in the axis which has more noise. The encoding looks very similar. So up to here, you would have this state. Now what you do is you apply 3 Hadamards, and what you end up with is your encoded state in the other axis. And to measure the parity is very similar, but now you have to think about it in a different way. So believe me also on this, it's really easy to prove that by reversing the CNOTs and by changing the measurement axis, you are actually doing the same. You're asking if the parity or if these two states are in the same state or if they are different. Because if they were in the plus plus and a set error happened there, which flips the plus to minus, then this propagates through this CNOT and lights up this guy. And that's your syndrome. So this is the same thing in the other axis. Now these are very simple, let's say, concepts. And this very simple example already tells us a lot of things about quantum error correction. Yes?
A small question. Why do we need to measure the parity?
Very good question. Because there's no other way. We have to extract information from our logical qubits somehow. And we want to do this without measuring it. So the only way to do this is adding more qubits that are actually kind of entangled to our logical, which we are then measuring to see if the error happened. Maybe this is not so clear now, but maybe in a second it will be a little bit more clear with other examples.
Okay.
And these very important concepts from this slide would be first the distance, because distance is something you're going to hear a lot. What's the code distance? So it's the amount of errors you need so that your logical information is corrupted and you cannot even know about it. So in this first example, if we have a 0, 0, 0, and we have 3 errors, this even works for the classical case. So imagine we have just 3 zeros. If we have 3 errors, and this gets into the 1, 1, 1, there's no way we can know an error happened. And that's what we call the distance, how many errors it takes for us not even to notice. And in this case, this is the bit flip distance because it's the amount of X errors that it would take to flip the logical state. But in the phase flip distance, what we would have is a distance of 1. It would only take one set gate in any of these guys to get from this state to this other state. Why? Because the set acting on the 0, 0, 0 gives me a +1, but acting on any on the ones gives me a minus. And now I'm changing the logical state right there. Another concept is the detection. So how many errors can I detect? This is in general d minus 1, being d is the distance. And so here in this example, for the bit flip distance, we would be able to detect at most 2 errors. Why? If I receive a 1, 1 and a 0, I can have 2 possibilities, either 2 errors happen or 1 error happens. So we can detect up to 2 errors. But how many can we correct? We can correct only 1. Because if 2 errors happen, we are not going to be able to distinguish it from the 1 error case. And we're just going to be assuming that 1 error happened. Because if we have 0, 0, 0 and it flips to 1, 1, 0, we're going to think that it was a 1, 1, 1. And when we're only going to be able to correct up to 1 error. Now, this is a very simple example. This is really the 101 of how to think about this. Because in general, we would like to correct both of these guys, not just to choose one or the other, right? And this is where the shortcode appears. This should not be there. Just ignore it for now, this lower sentence. So what we're gonna do is we're gonna take both ideas and we're gonna do it at the same time. So in this first part, the C-nots and the Hadamard's, they maybe look familiar, is the encoding for the plus, 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 and then you're gonna even add more to just do the second encoding for the bit flip. And how this looks is not a so simple circuit. So we start, imagine our state here is a 0 or a 1. Up to here, they will transform into plus, 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 or minus, 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 depending on what you started with. And in the second state, this is gonna be much, much bigger. And every of these pluses that go here, here, or there are gonna be one of these blocks over there. So as you can see, or very important conceptual ideas about this is we have now a very big superposition encoding our qubit, and that's gonna make it more strong against the noise. And now the game is, this is really nice. This is the short code because now we can correct both bit flips and phase flips. So imagine we have this state right here, and an error happened on the first qubit. This would flip 0, 0, 0, 1, 1 to 1, 0, 0, 0, 1, 1. We measure the parity between these two guys using an ancillary qubit, and we actually just we play the same game. We ask some questions, we get some syndrome out, and then we know what corrections we want to apply. Now the super nice thing about this is that if you're able to correct single X errors, single set errors, and single X set errors, which is also this case, I didn't mention it, but you can correct X set errors, which is a Y error. Maybe it's not so simple to see it from here, but believe me on this one, then you can correct any single qubit error. So you can imagine that we have this block sphere, this abstract mathematical construction, and our qubit is a vector pointing in the surface. Now, these X flips and Z flips are rotations that are just 180 degrees. And it just seems like really fixed stuff. Like what happens if my vector just moves slightly in one direction, like 1 degree in some other direction, which was not my information. And also for you to get just the feeling for it, imagine like I wanted to have this information and my qubit moved a bit. Then we are not able to correct that one because I was only able to correct 108 degrees. No, but the good thing about this is the following. Every time we are using the ancillary qubit, this extra qubit that appears just to ask questions, this is actually doing one more thing. And this is illustrated by the following example. Imagine we have a state 1, and imagine it deviates a little bit. And I express this deviation as, let's say this epsilon is very small. So with a 99.99%, we're going to measure a 1. And with a very small probability, our state is going to be flipped. But we have now this superposition, and this block vector just moves slightly. But in practice, when we measure this state, we're going to have a 1 or a 0 at the end of the day. And this actually means that a bit flip happened, and this means that nothing happened. So that's the whole thing. When we measure, and by playing this game of measurement, we are collapsing our state to those options where the error either happened or not happened, but it cannot be in between. So if we had the 1, in practice, what comes out is just a 0 or a 1. Maybe we had some very slight, super small error that, no, but we're in general just gonna say, did I have a 0, did I have a 1? Oh, I had a 0, but this is the probability of the bit flip. So we have a bit flip with probability epsilon square over 1 plus epsilon square. So, yes?
Just to understand this really quick, in the parity check before,
yep.
Basically you're saying what's happening is when you do the parity check, strictly speaking, there are some small permutations, so there's a certain chance there would be a parity, sometimes there would not be. But by measuring, you forfeit, exactly. Now it is 1, and that is why you can discretize.
Exactly.
Okay.
Exactly. That's exactly right.
Understand.
So these ancillary qubits, it's actually collapsing our logical state into the case where either X, Z, or Y error happened, but there's no option in between. Because if you would not touch your qubit ever, then this vector could actually just slightly move in its own direction. But by collapsing it, we are discretizing and digitizing the errors. So again, projection is both a curse and a blessing in this way. Like it's saving us from an infinite possibilities amount of errors to just 3. And if you're able to correct these 3 guys, your qubit is in principle safe. So again, quantum error correction is possible with a few complications. And these complications, the actual, I don't know if you got the feeling for it, but I'm just saying we add more qubits and then we add more qubits and then we add more qubits. So let's think about this for a bit, because there's something that we should stop and think about what we're doing. First of all, I said we are going to add some extra qubit. We need some CNOTs. Like this is adding more and more resources. Like we need 1 qubit, we need some CNOT, we need some measurement. And imagine before I just had 3, but imagine I have 5, then I have to add a lot of these guys with a lot of CNOTs, a lot of measurement. So this is actually, we have to think a bit about this. In this case, just to correct 1 error, we would have to have around twice as many qubits just to be able to measure their syndromes. However, if we want to correct both, then it already is a square overhead. So we need a square amount of qubits just to be able to correct and detect the errors. This is a lot. This might not sound like a lot, but it's a lot. Why? Because before, for example, I said, if I have 3 zeros, then my failure of transmitting a 0 is 2.8. And the more zeros I put here, this failure risk is going to go down and down. But in quantum, again, we're a bit different. Why? Because imagine my qubits are really bad. Then the more qubits I add, the worse it's going to get. Like there's no way I can make a useful thing out of very unuseful stuff. So there's this thing called the threshold. And this means the probabilities of having a fault, having an error, have to be below some minimum so that this game actually works. If my qubits are really, really bad, the more qubits I put in to correct, to measure, anything, like even the extra one I added, if that guy is adding more noise, maybe that measurement is giving me bad outputs and I'm correcting in the wrong way. So this can get messy really quickly. So all of this game is assuming that your qubits are good enough. They have to be at least good enough. When they are below this threshold, then it's okay. Then you can play this game. Then you can put more, and then you're gonna be more robust against the noise. There's this formula that says your logical error, which means the error of this super strong qubit that it's against the noise. It's gonna be your actual probability of each single qubit making an error between this threshold to the power of your code distance. And that's a really nice formula you maybe will see in the literature. So there's going to be a very large overhead unless P is much smaller than the threshold. Because if you're really close to the threshold, let's say in the good way, which you can play this game, you're going to need a lot of qubits. And I mean a lot of qubits to have a decent one. But if you have that every single qubit is very good, then it won't take you a lot to have a decent or a good logical qubit.
How large is that threshold?
It depends on a lot of things, and that's a really good question. This means, for example, that depending on how you encode your information, this threshold is not something universal. So for every specific case, it depends. For every specific architecture of your qubit, code you use, and everything like this depends. So this is just for, in general, having this threshold idea in the back of your mind. So I thought when doing this presentation that if we're going to talk about quantum error correction, I have to talk about the surface code. This is the thing that is now worldwide most used. This is used by Google. This is used by everyone. Most labs, they use the surface code. Everyone is talking about how to use this thing. So I'm going to present it to you because with all the knowledge I have presented here, you can maybe get already what these experiments are trying to show. Here I'm going to show you an experiment from the UTH, the university I'm studying in, where they took many qubits and they put it in this grid. And this is actually what I showed before. So let me walk you through it. Before I said we're going to do some encoding that look very big, and we're going to protect both phase and bit flips. But then one has to think about how to do this in real life, in a chip, where qubits, they don't all talk to each other. They just talk to their neighbors. And so one has to be careful about this. So people started to do very smart ways of encoding their info. And for example, this is one example. This is the simplest thing you can do, where your qubits have only neighbors connectivity. And you have here in red 9 qubits that are going to be your data qubits. It's called data qubits because they store your quantum information. All the other qubits with colors, both blue and green, they're there as auxiliary, and they're going to be asking these questions about parity in both x-axis and z-axis. So to put an example, this set 3 will measure the parity in the set basis of these 4 guys. And as you can see, actually, if you just take the green part of this plaquette or the blue part, they are asking all qubits how are, more or less all qubits, how are they doing in both axes all the time. So for you to see what these chips look like, and this is a actual picture of the chip, of some chip with superconducting metal. The little dots are actually the qubits. You can actually see how this translates there. There's very light colors that show it, and the colors are actually there just for the drawing. Actually, this has no colors in real life. It's all gray, but you can see how a lot of pulses go into these qubits and everything like this. But the game we're trying to do is to protect this logical qubit from the noise. So people start to think about this whole block about my logical qubit. So my logical qubit is composed of many noisy qubits, and hopefully this is better than just having one. So hopefully that's the most important question. Hopefully this whole thing that I did, encoding everything like that, hopefully that's better than just having one that is very noisy. And the checks they do, they are exactly the same as we saw before. Yes?
In that diagram, do the nodes represent qubits?
Yes. In this diagram, these nodes represent qubits, and they are the same as these dots over here. Yes. And so the checks are actually the same as before. But now the only difference is they are checking more things. So our ancillary qubits, which are living in this first line, they check the parity between more guys, more different qubits. But it's the same game as before. So now these experiments look a lot very complicated, because these are figures straight from the paper. They are gonna try to do this circuit for all of, like, that's only for one of these squares, but you have to do it for both the squares and both triangles. And then you have to do the x. These squares. So the circuit is not simple. It actually translates to this mess right here. So don't be scared, but this would actually be what you would be doing in real life if you wanted to do this experiment. And you don't see any C-naughts. Why? Because, okay, this is a lot of technicalities of how the experiment. They cannot do C-naughts, so they do some equivalent to the C-naught, which is this C-set gate, whatever. But the idea is the same. So you can believe me on this one, that it's the same. And then you go to the conclusion. So what happened here? And yeah, it's really complicated. You see these graphs, you're like, okay, am I doing better? Am I doing worse? After some time, you see here in the dashed lines, they put one qubit, not logical, just physical, one qubit. And this is how it decays in time. Let's say this is the expectation value of the set operator, which would then represent the information you're storing in that axis. You see how that is decaying through time. And then you see in solid lines how my logical qubit is performing. And this is actually worse. So after all of this you've been through, after multiplying everything, you're actually doing a little bit worse than just having one. And then you realize, okay, what have I done? But no, it's not so bad news, because if you just increase slightly your physical qubit, maybe you are under the threshold, and then you are better already. So this is what happened with Google. Last year, they were super excited about this. The world was super excited about this because they had this massive chip Here you can see how they have many more qubits. It's not just 9. Here they have 7 by 7, 5 by 5, or 3 by 3. And they actually, let's say, they had more resources, so they asked more complex questions. They said, okay, now my qubit, let's say, is going to be this, and then this, and then this. Is it better? Is it worse? And they perform a lot of analysis on this. And if you forget about this, which has a lot of lines, in this small plot over here, you can see that when they increase their surface distance from 3 to 5 to 7, their logical error is going down and down and down. This is great news. Why? Because remember the algorithmic part of all this, what I said, we need 10 to the minus 17, that's huge. Like in principle, if you would put this axis all the way to minus infinity, you can follow this line and actually get there. Like there's a path to get to 10 to the minus 17, and we know how to get there. We just have to follow this line. It's not so simple, but that's the game everyone is playing right now. And this is it. So the blue patches over here, they are the same as before. They are measuring their neighbors over here, and they are asking this parity question. Now in this graph over here, you have the error probability as we advance in time. And you see that as increasing, and this may be confusing, but it's not, because the more error, from the time you initialize, the time goes by, and then you can have more and more errors in your qubit, so you're performing worse and worse and worse. But the good thing is that there is this red line is for the distance 3, which is this small patch. But already when we go to distance 5, which is this blue cyan line, which is this big patch, then we're already doing better. And then if you step one step further to distance 7, the logical error rate goes again down. And this is the game we want to play. So I think you more or less get it. Is there any question? Again, this is not a technical talk. This is just for you to get some of the main ideas. Now let's talk about repetition code with cat qubits. So maybe as you can see how is Alice and Bob, this French company, wanted to build their logical qubits. First of all, to tell you a little bit about what we're doing, I have to present with our qubit, our technology, which we will do. It's super nice. Why? Because usually we have bit flips and phase flips. But if we just look at data from the qubits we saw before for Google and this other experiment from ETH, these are transmon qubits. If we look at the time it takes for an X error or a Z error to appear on average, this is in the microsecond regime. And we look at cat qubits, we see that in the x-axis is 10 seconds, and to get a Z error is 1 microsecond. Anyone notice something really peculiar about this?
They are different.
Exactly. They are very different. And indeed, for the X errors, we are 10 seconds. Like it takes 10 seconds to have an X error on our cat qubits. And this is very nice because in 10 seconds, believe me, you can do a lot of things, a lot of things. And in quantum, you can do super complex algorithms in these time scales. So in principle, if our operation is less than 10 seconds, we can say, okay, I don't have any errors.
It means that on TZS, it's a little bit shorter than transmon qubits.
Exactly. Yeah, that's another good point. We are so much better in the X errors, but we are a bit worse in the Z. So let's look at this. How can we get through this? But cat qubits, it's for you to understand the ideas. We're damping all the noise into one of the errors. So let's say we really want no bit flips, but we don't care about phase flips. And this is how we construct the qubit from the beginning. So our block sphere looks a bit weird. And this is because our zeros and ones and plus and minus are not just regular states. These are, I don't know if you're familiar with the concept of coherent states or cat states. If you're not, no worries. What this looks like in practice is that just a 0 or a 1, just for one qubit, one physical qubit, is just this massive superposition that looks horrendous, but it's not that much. Just you can imagine this as coefficients. These are our quantum states. It's an infinite superposition of these states, and that's going to be my 0. And in the same way, for the minus cat, this is gonna be my, I mean, in this case, is the plus and the minus. But so that you can see how my qubit is not gonna be just one energy level in our quantum system, is gonna be a superposition of many of them. And what this is gonna do in practice is, for some very complex math, you can actually do. I mean, it's not so difficult to see that we don't have bit flips, or bit flips are really hard to get. We just have phase flips. And this means that to go from here to here, it's really difficult. Or let's say takes 10 seconds. But from go to here is quite easy. And you can more or less see this, like the drawings look familiar, or like they look really slightly or really similar. And these guys, not as much. I mean, but if you are not familiar with the concept of coherent state, maybe it makes no sense. But so this is just to say that we have already a more complex qubit from the beginning, not just one state. Because in the transform, maybe this makes it a bit more clear. We have some potential, and this is our energy eigenstates. And here in the transform qubit, we say we're gonna put it in the fridge. We're gonna go all the way here to the ground state energy, and we're gonna forget about these upper energy levels, and we're gonna just use these two guys. And this is really just two energy levels of our system. But in cat qubits, we have the quantum harmonic oscillator, maybe you saw in class, that is equally spaced between all of the levels have the same distance between each other. And this means that I can actually, when I send a pulse or I send some photons with this energy, this is gonna bring the 0 to the 1 level, but it won't stop there. Like it will climb up. So you cannot address just two levels. You always address this thing as a whole, more or less. And this creates these kinds of superpositions that have very nice properties.
So
Yes?
in this case, how we can identify which one is bit 0 and which one is 1? Because in transmode, we have a 2-level.
Exactly. Yeah. There's also other ways to distinguish between superpositions. Like this is also another whole field of quantum optics where there's a lot of these states which are very special. Like the coherent, for example, is one very special case that you can manipulate, that we know how to do it. So you can think about it in this way. We're not interested anymore in this guy or this guy. We're interested in the whole superposition, in the whole ladder, and we're treating it as a whole.
Yes.
So you can also imagine that to perturb the whole thing versus just to flip this guy to this guy is much more difficult in this case, more or less.
Okay, but we want to turn it into the bit 0 or bit 1 in the end. So because on information based on
Perfect. So remember the image I had before of the encoding and decoding? This would be the encoding step. You put a superposition of a special superposition of all of these states. And in the decoding step, you have means of reading out this superposition to say, I had a 0 or a 1.
I see.
And things like this. So that's a really good question, because fundamentally our qubits already have like a built-in property, a built-in functionality that has already error correction from the beginning. So this is why cat qubits appeared as a really nice technology, is because, okay, I already built a qubit and it already has some really nice noise properties, and it already from the beginning has noise protection. In one axis though, the other one is much worse. So how is this trade-off? Yes?
Doesn't it become much more difficult to apply gates on this kind of particular?
You're completely right. To be honest, it's much more difficult. Like this, from the beginning, it's a much more complex qubit. You have to be more careful about a lot more stuff. You have many more components compared to this, which is really simple. So yes, the answer is yes. And you have to be very careful about the gates, because some gates, they convert your set errors to your X errors. For example, the Hadamard gate, if you put set errors, they will go to X errors after the gate, and vice versa. So you also have to be careful not to convert the errors you were very good at to the other errors, more or less. So yeah, everything gets a bit more complicated, and that's the price to pay, to be honest. Yes?
I can see how bosonic qubits have a longer time for the TX time. Based on the technology.
You cannot understand, or yes?
No, I don't understand. What you explained, right? About how the time for TX rates will be much longer than
Yes, exactly. So you want some intuition about why is it?
Yeah, why?
Yeah. Yes. So if you see this picture, and I don't have the right slide for that question, but maybe if it's to go from. So are you familiar with the concept of coherent state?
Yes.
This is the electromagnetic pulse. Like to go from an alpha state to a minus alpha state, you have to displace your state by 2 alpha, and this means quite a big noise. Like to be able to displace your state exactly from here to there, it takes a quite strong electromagnetic pulse. Whether maybe from here to there, it's not so hard. But the amount of energy it takes for you to go from here to there, it's very high.
So it's not based on energy level, because in transmon, right, the axis depend on the energy level between two states.
Mhm.
If it's very far, it means it takes very long time to go down, to fall down on the ground state.
Yeah. So the way to think about this is slightly different. Is with these Wigner functions that tell you about this whole superposition, and this is the drawings over here. And one can actually draw the potentials. There was a very good slide about this, but you can actually see how the amount of energy it would take from here to here is this is more or less like a double potential well. In the 2 nodes, it's where these 2 guys live, and to go from one to the other, you had to climb up the potential hill to go to the other one, and this is very disfavorable energetically.
Maybe I have a question close to this. In
Yes.
Transman, maybe the next slide where so in Transman you have this leakage problem, right? I mean, other qubits. Do you have the same thing in cat qubits where like your current state is not exactly?
Yeah, and I think it's much worse because you can have. So we have infinite many degrees of freedom, and this infinitely many flavors of things you can escape to. For example, here there's a discrete handful. But yes, so this is also a problem ones to have to really think about is just to have this superposition and not other ones. We just want this. But this is not something impossible. I'm just saying it's really hard, and we are working very hard on it. But it's. But let me show you why to make this effort. So the trade-off here is bit flips are suppressed exponentially, and phase flips only increase linearly. So we can exponentially suppress one, we're only linearly increasing the other one, and this is really nice. I mean, because we have gained a lot of noise bias or noise protection in one direction without just slightly making worse the other one. In this x-axis, what you will see is the photon number, and this over here is your lifetime. So our qubits, actually these blobs you saw before, they indicate the distance between these 2 blobs indicate how many photons you have. So our technology is based on a resonator that stores photons. The more photons you have, so this is this axis, the longer the lifetime is gonna be for your bit flips, and the worse it's gonna be for your phase flips. But this is linear, and this is log scale. So you can find some sweet spots in between where your bit flip is really, really good. Your phase flip is not so bad. Yes.
When it's saturated after.
Yes. So this is actually experimental dots over here, and yeah, in experiments we saw that it's saturated, but this is an old graph. I'm gonna show you the latest one, but this was not because of the theory. This was for some other reasons that we later found out. So the trend goes up. So to remind you again, what we are saying here is, okay, we're not gonna care about bit flips. Let's just say we need to correct for phase flips. At least we saw before. This would just mean that we have our data qubits here in the solid lines, and we are gonna place in between some ancillary qubits that are gonna measure the parity between every 2 qubits. And these over here are gonna be our cat qubit distance. Now every one of these guys is gonna be the superposition of a harmonic oscillator that already has some built-in quantum error correction. And by doing a distance like this, we're just gonna be able to correct for phase flips. So our logical states are gonna be plus, 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 minus, minus, minus. And our logical operators, which I didn't touch a lot about, is the way to turn a logical plus into a logical minus, etc., etc. And the syndrome extraction would look the same as before. And that's the thing, that doing this in 1D is much more simple than doing it for a square with so many qubits as we saw before. And it was not only Alice and Bob that thought this was a nice idea. Yes?
So in this case, we need only do implement the phase.
The phase repetition code. Exactly.
Exactly. We do not need to do, right?
Yeah.
Okay.
Yeah. And the exact trade-off, if you want the specifics, is over here. So by doing this, now our phase is really strong because we are putting a lot of redundancy in the phase. So the phase flips are suppressed exponentially, and the bit flips only increase linearly. So there's two layers. The first layer, how we construct the qubit, already has quantum error correction. And then we actually do redundancy, and that's the second layer. And we have to find some equilibrium between these two that will make our errors very like disappear, and we can actually do calculations. So we were not the only ones to think that this was a good idea, and I wanted to show you actual things that were done in the lab. This is from Amazon, and they did exactly this idea where they have cat qubits here in blue, and they have transmon ancillary qubits here in orange. They are measuring the parity between these cat qubits. And these flags you see here is, for example, in the case set error happened here. And remember, this is set error because we only correct for phase flips. This is gonna light up these two guys. Are gonna say, hey, an error happened here. And because only these two guys flagged, you know it's here, and then you can correct for it. And when you put this on a chip and you study all the properties, it's not so simple to do it, but one can actually demonstrate that. Forget about the alpha axis for a moment here. We can see how they just took these three guys and then they took the 5. The game more or less like Google did in Amazon. So by taking just these 3, this is the red and the blue. This is some logical error phase flip. And when they extended to the whole string of the 5 they had, the whole logical error goes down. And that's what they mean here as if we put more and more, we're gonna do much better, and we can climb this ladder down to some other lines that are gonna go farther and farther down. Yes.
In this case, ancillary qubits are just normal transmons, not.
Yes. So yes, there's a lot of
grid type.
Exactly. In this case, they thought it was a really good idea to use transmon qubits. One can also think that it's a good idea to have cat qubits also there. Yes, so there's really a lot of options trying to get the most out of this. Yeah, so don't get too much into the details of these experiments. I just want you to get the general gist of the game. But now I'm going a bit over time.
No, it's fine. It's fine.
Yeah, okay. Now the big point here is one thing Alice and Bob is thinking about is in the long future. So let's see how these two approaches compare. Let's see how the regular transmon compares to cat qubits, etc., etc. And yes, I'm not saying anything about trapped ions, neutral atoms, and everything like this. But in every platform, they are more or less trying to also do some error correction. That's more or less what the industry is shifting towards. They are realizing we can maybe not do perfect qubits, so we have to actually deal with these errors. So people are starting to compare the approaches, and let's see how it goes. So yeah, quantum error correction, as I hopefully motivated, is qubit expensive. And this means we have one noisy qubit, and to get one error free, we need this chip that is just one. This is one close to perfect qubit, logical qubit. And this is what you would need to run your decryption algorithm.
So, cat qubit, right?
No, this is transmon qubits.
Okay.
Exactly. Yeah, thank you for the question. This is just for Strasbourg. You would need 1,000 of these guys. But yeah, with today's technology, you would need a full cryogenic system and 3 dense control racks to run this logical qubit. So actually, this chip is not something I can have here on the top of my table for it to work. I need these fridges. I need these control racks sending pulses to the chip. I need the machines that actually make the fridge work, and these are not small. So let's say we can put it in this room. We could put it over here. Okay, that's my one cube. So yeah, this would cost me about $10 million, and it would consume up to 50 kilowatts. So it's also not so cheap, right? And I just have one logical qubit. So what can I do with it? Nothing. I have a very expensive machine over here just to do nothing, maybe to put some news over there, but that's it. Let's put this more realistic scale. Let's say we want 100 of these guys, right? Now we have, okay, you just need to find $1 billion, 1 kilowatts, 1,000 kilowatts to power this thing. And yeah, this would take like an entire plant. This would be like this entire plant full of these machines. With all the technicians working on it. You can imagine the logistics, crazy logistics about this. But yeah, I had the money, I had the infrastructure. Yeah, it's there. What do I have? 100 qubits.
There are more jobs in the future.
Yeah, more jobs for us. That's completely agree. Well, maybe it's very expensive, right? And at the end of the day, with all of this huge mess, I just had 100. And yeah, what can I do with 100? Not a lot. So yeah, maybe I can start doing stuff, but it's not so like you haven't gone through any breakthrough. So yeah, let's run the Shor's algorithm on standard error correction. Like let's break some decryption. Let's make our computer super nice. Okay, so let's take this plant and like make a lot of plants of this, and let's put it like that, and then you're gonna build this massive skyscraper. It's gonna be 750 meters. Every single one of these layers has a floor full of cryostats, and that's more than twice the Eiffel Tower. That's quite an impressive. That's quite an impressive building. So how do you power it? Easy money. You just power it to a nuclear station, and yeah, I have all the energy I want. This cost me just $10 billion, just like that, and 100s of megawatts. Yeah. From Alice and Bob, we think this is a bit crazy too. This is where we all want to get, right? We want to do 20,000 logical qubits. We want to be able to do anything we want. But what's the price to pay?
Maybe we need to implement on the moon.
Yeah, on the moon. Go to the moon and
I guess that these qubits wouldn't even be connected together because you have
you have to
100 qubits in each plant. So how do you manage to connect them?
You have to think about how to connect them also. So you can imagine these fridges are connected through some, I don't know, fiber links or something like that. And yeah, you also get the difficulty of this. Like, and then you have to connect the floors. So the whole plants with other plants. Really complicated. But no, I mean, to be realistic here, this is the approach that some companies are aiming for this approach. And I don't know if you're familiar with PsiQuantum, for example. PsiQuantum, their computer, their quantum machine is based on photonic quantum computing, which is completely different. But how they are doing their correction is exactly like that. And if you see their installations, it's a field, like a football field, and that's just like a couple of logical qubits. So yeah. So in Alice and Bob with cut qubits, we only have one error left. So we don't have to go to 2 dimensions in the repetition. We just have to do 1 dimension. This is what we are saying. We're not saying it's gonna be easier. We're just saying we can do this. And like our chips would look like this. But there's something really nice about this. This is and again another graph saying that our bit flip lifetime, and you can see this on our webpage, actually reached 1 hour. Just this was a finding last month, where we have 1 hour until the first bit flip error appears. So we're really strong in one direction. So yeah, what we do at Alice and Bob is we don't need this surface code. We just need some repetition code like this in 1 dimension. And actually, one thing about this really hard, and you can read this paper, it's really interesting, how if you take this string and you fold it and you allow some other connections, maybe you can have more logical qubits with less physical. Like, yeah. And then you build these strings going like a snake that have multiple logical qubits. Only by allowing extra connections between distance. So here we folded the string and we allowed some extra connections there. So if you do the numbers, this would be like a 200 times reduction versus this approach. Like this is 200 times less qubits. Yes, they are all cut qubits and they are more difficult to manufacture, but this is 200 times less than the transform qubits. And what this would compare to is, instead of having this huge thing that also like it's going up the screen, you just have your nice plant over here connected to a wind turbine. I mean, yeah, this is a bit, so that you can compare the scales of the approaches. But this is a very visual way to see it, actually. Like, people are aiming to have some useful machines in 2030, and people are taking different approaches to do it. At Alice and Bob, we believe that there's an efficient way to do stuff. Maybe it's not the simplest one. Maybe it's actually one of the hardest, but we have to do it in a logical and reasonable way. And this is almost the end of the presentation. If you want to know more about how we are gonna do it, I suggest you scan this QR code. It shows the exact steps Alice and Bob tries to follow to get there. And so the company is also offering many internships soon. And as I said, we're growing super fast, very fast, and people are really motivated about it. I really like the company personally. And if you have any questions, I'm also super happy to help. If you want to follow me on LinkedIn or whatever, we can have a nice chat. I mean, I'm also a student, like probably most of you guys. So I'm also just got in this world, and it's really exciting, actually. It's really, really nice. So I hope you liked the talk. Maybe you got some ideas about error correction that now you're gonna practice. So thank you for your attention. Thank you. Yes.
So you mentioned very briefly at the ending, so the code you're using is a particular quantum LDPC code, right?
Exactly.
Based on personal curiosity, does this one fall under the category of expander codes?
Sorry?
Is an expander code?
Expander code?
It's a particular type of quantum LDPC code where basically the way your qubits connect, it's a graph which has some expansion properties. And often LDPC codes that have such expansion have fast decoders, for example, and good good growth of data qubits versus logical. I was curious.
Yeah, I'm not sure I can answer the question. Maybe actually in the paper you can see this. As far as I know, I'm not sure if it's the way you put it. Like, I also took a look at the paper and it doesn't look like it. But as I said, so sorry I cannot understand or answer the question. Yes.
So you just mentioned that Alice and Bob is not only the company who want to operate the cat qubit, right?
Yeah.
So we have Amazon as well. Right?
Yeah. So what about that, you mean?
I mean, there are how many companies?
How many companies?
In overall?
As far as I know, it's just Alice and Bob and Amazon following this approach. And there's other ways to encode information in multiple layers of a harmonic oscillator, and there's this GKP states. I mean, other people are trying to make from the beginning really smart qubits.
Oh, yeah, okay.
And that's the different approach, like not just copy and paste, but just actually take time to make a really good qubit to then scale it up. So yeah,
please.
Yeah, so the question maybe closer to the first one, so I don't know. So you have this very nice comparison between the like scalability of this standard surface code versus cat qubit plus one-dimensional code. So what about the cycle time? Because I mean, as you say, there might be easier decoder if you have a simpler code. So my question is, do you know about is the cycle time maybe also shorter or faster or not? Or
I would expect this. This is an open question, and that's a really nice question. We are actually in means of understanding, but as you can see, we are just going 1D, and this is in principle a bit easier to decode, which maybe doesn't mean faster because we have to take into account our measurement times and everything like this. So that's a
Yeah,
really,
yeah, like what is the measurement time of these cat qubits and so
yeah, exactly.
compared to like number transforms and
Yeah,
so-
that's a really nice question to bring up, and I think it will maybe some future results will reveal this question. But you are absolutely, it's absolutely fair to ask these questions about comparing gate times and or decoding times and everything. So yeah, thanks.
So maybe just because at the beginning you had this time estimation for Shor's algorithm of like 1 week or so. Is this based on some estimation of the cycle time, or is it generate?
Yeah, but that's not for cat qubits. Like, that's from other papers of how long it would take for. I think that's based on transforms, to be honest.
Okay.
But,
Okay. No problem.
Yeah. Yeah, thank you.
Any more questions? Online participant on site? Yes.
Hello. Hello.
Yes, please.
Can I have a question? Could you hello?
Please say.
Sorry, do you hear?
Yeah. Thank you for your nice lecture. I mean, I just have a question. Could you explain again what is why the DZ and DX is the DZ is quite large, but DZ is so small. So is that a trade-off? So is that a trade-off? So what's the root from the physical hardware? Why we have that trade-off?
So what's the is your question? What's the physical reason we are having a trade-off?
Yeah. What's the physical reason why we have that trade-off? Is if there's a trade-off or the limitation of the hardware, and yeah.
Yeah, maybe let's look at the slide again. I'm not sure I can give you the exact technical things why this trade-off exists, because for this you would have to go into the quantum optics technicalities of this whole. But if you can see, I mean, yeah, maybe I cannot give you the right intuition, but this trade-off can be played. Like you can actually measure how, with the scaling your photon number that your resonator has, the more photons you are storing, and this you can just measure if you have the right equipment. You can see how the more photons there are in your cavity encoding for a coherent state, then the longer your lifetime will be in one axis, and the shorter it will be on the other. But the scalings are quite different. So one is going to be exponentially suppressed, while the other one is only linearly increased. And I'm sorry if I cannot give you the right technical intuition, because I think this is not so simple to understand either way. But yes, so if you were just to have this equipment and you can measure this in the lab, actually this is what you get. Like there's a trade-off. Inherently, this comes from the quantum mechanical properties of your cat qubit, I think. But yeah, I don't know if this can a bit of, yeah.
Oh, and one thing that the surface cost is applied for all quantum computer platform, or just within the superconducting qubit. Can that apply to the like neutron ion or trap ion also?
I'm not. I don't think any trap ion company or neutral atom company is looking at surface codes, because what they can do much better than the surface code, because they can actually connect ions to other ions, and it doesn't matter where they sit in these traps that they sit into. So the codes they actually play are more complicated, because they then require that the qubits are connected next to their neighbors. They can connect any qubit to any other qubit. That's one of the advantages of their platform. And the codes they run are different than the surface code. They're more complicated.
So it looks like the trap ion architecture is quite have advantage currently.
Sorry?
I mean, it's so because the connectivity of the trap ion or neutral ion is quite large. I mean, yeah. So does mean that platform has the advantage currently on the implement the quantum, do the quantum error correction?
I don't think it's an
Yeah,
advantage.
I mean, I just would like to know the situation currently on the which platform has the advantage on the quantum error correction, or the
The thing about the traptines is they have other challenges, like trapping more and more ions is challenging and things like this. So every platform has their own difficulties. As far as I know, it was only Google that actually proved that you can have an error correction code under the threshold, and this was last year, and it was Google with the transmol qubits. I don't know if up to now some other company published some paper. I don't think I'm aware of, but that's the current situation. Like I think companies are doing it, but maybe not. We don't have a lot of results.
Oh, okay. Yeah, thank you. Thank you, ma'am.
So, from if I understood it right, like you said at the very end, like LDPC codes are better than surface codes, like in theory, right? But we are like trying to make it a practical approach. Like, why is it better? Because of the encoding rate?
Yeah, exactly right. Like the encoding rate is much better, and this means that with the same amount of qubits compared to a surface code, you have more logical qubits.
And also, will it be like less expensive in terms of like overhead or like fees?
Yeah, completely. Like the overhead price is 200 times less. As I tried to motivate here, like the overhead is much less than just with the surface code, and that's the most the greatest advantage of going to LDPC code. Like you need many less qubits, and you will need these features, and maybe one can fit all this into one large chip, super large chip. We'll see.
Why is it difficult to like the practical approach of it? Like, why is it more difficult for the practical implementation of it than surface code? Do you say? Like, why?
No, I'm not saying this is more difficult. I'm just saying the manufacture of every single qubit for CAD qubits, it's more components. I mean, if you I don't know if you have in mind how the surface code chip looks like, but it for every qubit they require some lines going in to control it. But for the CAD qubit, these lines are a bit more, and the elements of the CAD qubit there are more elements that you have to take into account. And yeah, so the fabrication is it's more complex.
Okay, you're just talking about this in terms of just CAD qubits, not like I'm like general, like not if I say not CAD qubits, like other like general qubits. In terms of that, will it also be more difficult for LDPC codes?
So anyone could do LDPC codes in principle, and transmog qubit can also do LDPC codes. But the thing is about LDPC codes is that they just correct one error. So they just correct for the phase flip. So I mean, with transmogs you can also play this game of going to LDPC code, but you are neglecting completely one axis of errors, and that's gonna kill your qubits every time. I don't know. Is this answering your question? Maybe I didn't understand completely.
Staying around, no way.
That's okay.
Is there another way? Sorry.
No. I say you're staying around.
Yeah, I'll stay around if you want to. We can chat later.
So thank you, very nice presentation. Thank you. So right now we're moving forward, moving on to our hand-on section from Muna Said from University of Oxford. Please come in.
Hello, everyone.
Yes, hello. We can hear you.
Hi. Let me share my screen and then we can start. I hope you can hear me.
Yes.
All right. So I'll be taking you through the hands-on lab practical on quantum error correction. And my name is Mona Said. I am currently doing a master's at the University of Oxford in quantum technologies. And I'm very interested in quantum information and especially how we can be able to correct errors in quantum computers with error mitigation and error correction. And as you all know, we are here for the Qiskit Fall Fest 2025 to celebrate the 100 years. And yes, so there's some useful resources that I'm sharing here on some of the companies that are progressing in quantum error correction, such as Riverlane, and then you also have Q Control, and also Alice and Bob. And I think some interesting things that the previous speaker spoke about was the CAD qubits, and then we also have Riverlane and Q control. Q control is actually using another technique called the quantum firmware, which is they combine that with error correction to be able to essentially correct accurately and also have less physical qubits. So it's like an interesting area of research that they're currently working on. And also some papers to help you go through and understand deeper what we learned today. There's a few that I've shared here which have some really interesting insight. And then, so what have we learned so far? Why qubits are fragile. We looked at bit flips, phase flips, especially with 3-qubit bit flip, and then we had the phase flip, and then the 9-qubit, and then we also looked at what Alice and Bob is currently doing. And also how quantum error correction can be able to scale to practical quantum computing. So the learning target of right now this session is just basically to get our hands dirty. By that I mean try and do some collabs and see and understand a bit more, because you can only understand once you've done the sheet. So you and so for the problem, the Jupyter notebook, we have the 3-qubit bit flip, which corrects the X errors, and then you have the 9-qubit, which does all of the errors, poly errors. And specifically, what we'll be looking at is how can we be able to encode physical qubits, add an error to it, and then detect it, measure it by that, and then also correct the error. And just back through what has already been discussed, I'll just move very quickly on this. Is we use a bit flip code, which is a 3-qubit encoding to be able to detect an X error. So we use redundancy. Just note that we're not cloning the qubits. And then another section which we'll be going through is syndrome measurement and correction. So how can we be able to detect if there's an error by using the ancillary qubits and then measuring it and then correcting. So here we'll be using the parity checks, which has already been discussed, which is really nice. And then how are some of the ways that we can be able to recover our original state. And then another thing we'll be looking at after the problems that we'll be working on during the Jupyter lab sessions is what are the limitations of doing repetition codes, which I will go through. And then we'll also have the section 2 part, which is the 9-qubit shortcode that I'll take you through. And if we have phase flip or if we have combined, which is the XZ errors, how are we able to correct them? And the 9-qubit shortcode actually shows exactly how we're able to do that. But this uses 9 qubits. There's another one that uses 7 qubits, which is the Steen code. So there's like several types of error correcting codes that have been developed that are way better than the 3-qubit or the 9-qubit. And essentially, the key idea, which has also been discussed, but I'll just take you through what we'll be doing for the labs, is the bit flip and the phase flip protection using concatenation. So we have the 9 qubits being encoded. So we first start with the phase flip and then we correct the bit flip. And the phase flip first, it's the outer part. So you have this first section, part 1. where we will encode the phase flip. So you have C naughts on the two other qubits, and then you'll have the H gates, and then you will be able to get them in a plus and the minus state. And then you also have the inner bit flip. Now this is where we'll be able to look at bit flip errors and how we can be able to correct them. And you will essentially encode it from 3 to 9. And essentially here, unfortunately, it's able to only correct one logical qubit with 9 physical qubits. So ideally, if you think about it, how many physical qubits we need to correct just one logical qubit is a lot. And we need to figure out a way to be able to use less physical qubits to correct logical qubits. And that's the current area of research that a lot of people are looking into. Yes, so key things I'll show you through the Jupyter notebook would be how can we be able to encode? How can we be able to simulate noise? So you add an error, either X, Y, or Z, and then detect the error with the ancilla qubits, and then also correct the error. And then we'll also look at other types of codes and stabilizer formalism. So we have the stabilizer codes, which actually represent quantum error correction codes. They use commuting Pauli operators. And then you have the CSS, which is it's quite long, the Caldebank-Shor-Stein code, which is able to separate correction of X and Z errors. And then lastly, we have the Stein code, which is the 7-qubit. Well, I talked about 9 qubits is Shor code, so it uses a lot more. But the Stein was able to show us how we can be able to use less. And then some key formulas that we need to remember is you have how is a code defined basically is you have NKD. N is the number of physical qubits, K is the number of logical qubits, and then D is the distance. And essentially, we can be able to correct up to the distance minus 1 over 2. So if you have 3 distance, you're able to correct what? 1 error. So this is basically, you can do the calculations of the 5 by 5 and 7 by 7. Okay, so I will take you through, apologies, let me stop sharing, then share, sorry.
Yes, please. Automate DPCs.
I will be able to take you through the notebook, and you can be able to do the assignments or the exercises later on, but to just have a kind of a rough idea of what's actually happening in this notebook. Right. So first thing first, we already discussed about what quantum error mitigation is and what quantum error correction is. And this specifically, I'll just be taking you through quantum error correction for the 3-qubit first. So this part is essentially just downloading the libraries that we need to be able to run some of the key areas and see how the code performs if you have errors or no errors and correcting them. And then we will import the specific libraries we need and the simulator, which will be able to see exactly how the performance is like. And this is to just help us suppress some of the warnings that we actually don't care about. Yes, so the 3-qubit flip code. So we talked about this where you encode 1 qubit into 3 logical qubits, and then you're able to insert an error, which is an X error, then you measure it, and then you're able to correct it. So here specifically what we'll be doing is the same thing where you have the quantum registers and the classical registers. And the quantum registers, we talked about it, I think it's holding quantum bits and it's able to store them and evolve quantum information. Well, the classical just holds the classical bits, which is now the ancillaries, and then it can be able to read and be able to make a decision on whether we need to apply a correction or not. So here what we essentially do is encode the key gates that we're going to be using, which is the Hadamard and the CNOT gates. And then another section now, which is part 2 of the first area, is add an error. So we want to play around with this and add an error and see how that performs. So if you add an error on this, so let's say for an example, I'll just show you here. I think you'll be able to understand it better. So an example, you have an error in the middle qubit here, data 1. So if you had an error in that, how were you able to detect with the ancilla that you actually have an error? So I think it was spoken about, but I'll just go through it again. So if you look at the first ancilla here is able to check for us the parity now between the first qubit and the second qubit here. So the key question you need to ask yourself is, do the two qubits actually have the same value or not? So, and then this second ancilla here is able to detect errors in the data 1 and data 2. And you can ask yourself the same question. So if the error occurred in the middle qubit here, the data qubit, so the first ancilla here is obviously going to compare the two qubits. And if it does have an error, then both the ancillas will give a syndrome of 1-1. So this ancilla, these two ancillas will give a syndrome of 1-1. So you will know that it's actually the mid qubit that has an error. So this is essentially how the theoretical background of what's actually happening. So we will have an error on the middle one, and then we'll be able to detect it. The third part is the fourth part, sorry, is measuring now the ancilla and seeing, okay, what are we measuring? Is it a 1-1? Is it a 0-0? Is it a 1-0 or a 0-1? And the ancilla will tell us, hey, it's a 1-1. So that means we know that it's actually the mid data qubit that it has an error. So we figure out a way to correct it. So that's essentially it for the first part. It's a very simple, but I think the code has to be in a very systematic way to be able to work that out. So the second part here, I left it for you guys to be able to figure out a way we can be able to correct errors. So you first run the circuit. We'll be using a sampler instead of an estimator because we need the values. And then you will analyze the final data and see what is the output. And then after error correction and before error correction, what is your state of, what is the set of the ancillas? And then remove the error from it and also run it again and see if there's no error in the circuit or if there is an error in the circuit. So you will put your answer, like when you work it out, you'll be able to have your answer here. And then a good thing is I added a solution. So in case you get stuck, there is a way that you can be able to work that through. Okay, so another part that I'll be taking you through is the section 2, where we talk about now the 9-qubit shortcode. And essentially here, we are just scaling it and seeing, okay, 9-qubit shortcode, it concatenates both the phase flip and the bit flip. So you have X, Y, and Z errors being able to be detected and corrected. Yeah, so here we first start by encoding. You inject the error, and then you extract the syndrome, correct it, and just verify your measurements if it's actually correct or not. So we have 9 qubits and 8 ancillas that are being used. And then the first thing first we need to think about is always have to look at the diagram. We say that the phase flip is the outer encoding. So you would start with a phase flip first, You'll start with the phase flip and then you go to the bit flip. And we'll first start by encoding the phase flip where you have the header and then you have the two C nodes. Another interesting fact that I'll mention later on is the stabilizers. So if you have an XXX, it measures a Z flip. If you have a ZZZ, then it measures an X flip. And then the phase flip we talked about is the outer encoding. The bit flip is the inner encoding. So you encode it into 9 qubits. And this is how you work it through. And then step 2 is you introduce an error and see how does that perform. So if you have a Y error here, which is a combination of both the bit flip and the phase flip error, for example, you have an error in qubit 4 somewhere here. So what does it tell you about the outcome? And then the third part is you have measurement of the syndrome. So you measure the syndrome and see if you have a bit flip, which syndromes are you using? As we talked about, is the use ZZ stabilizer, and then you're able to detect that. And then if you have a phase flip, which is the X-type stabilizer, here we will encode that and measure the X-type and see what our syndrome is going to be telling us. And according to that syndrome, if you have an error type that is a bit flip, which is an X, and then you have one Z ancilla, you apply an X get to that to correct it, because we already know that this is a Z ancilla has been detected, so it shows an X error. So you just correct it with an X. And then if you have a phase flip with an X type ancilla, then you apply a Z gate to be able to correct that. And then what if you have a Y error, which is a combination of both the X and the Z? You would apply both the X and the Z gates to be able to correct that. And then the final part is the verification, and where you now decode and measure your qubits. So if you measure them, according to the output, it should give you that, because the parities have already been able to tell us that you have an error here, then we fix it, then it should be able to give you the original state that you actually had previously. And then your task now is, can you be able to build up your own error correcting code with distance 3 for 3 qubit codes, and the T is 1. And it would be nice if you could also draw the circuit here, and you also calculate that. And then we have section 3 here, which just takes you through and helps you understand what are the current set of the art technologies that we have, which is the surface code, you have the QLDPCs, and many more. And so, as we talked about, shortcode is not the best efficient one currently, because if you think about it, if we are going towards more than 100 logical qubits or more than that, it won't make sense to have very many number of physical qubits that we cannot be able to work through, because they're exponential. And especially if you have errors, the bit flip errors and the phase flip errors, and each one of them has a different type of correlation to that. So the state of the art currently is quite different, and we're progressing very well. And the errors here usually create a defect in the syndrome. And so it's quite complex for the classical decoders, because we use classical decoders as a post-processing technique to be able to tell us where the errors occur. So there's something called the minimum weight perfect matching. And I think there's several new other ways. I think in Japan right now, they've found a very interesting way of going about a decoder. I'll send the link so that you can check it out. And then your task now is to use the Qiskit quantum error correction library and to define a 3 qubit bit flip code which is now the repetition code. So here is the area that you'll be doing your task. And then in case you do get stuck, we have a solution for you. Then you can have a look at it and figure out where you went wrong. In conclusion, today you're able to learn a lot. I'm sure you're all tired, but it's almost one of the last talks right now. So you've learned how quantum error correction can be used to actually detect and correct errors, unlike quantum error mitigation, which is mostly used with noise extrapolation, or you find the probabilistic error and then you figure out how you can be able to reverse that. And for quantum error correction, we're able to do this when we do redundancy of the logical qubits. So the more you encode logical qubits onto physical qubits, you're able to actually figure out, okay, my qubit has an error on this side, I can be able to correct that. And then we also built a 3-qubit bit flip code from scratch. And then we also learned the theory of 9-qubit shortcode and also built it. And I've also introduced a bit, and I think the previous speaker has talked a lot about surface codes and what is the current state of the art. So I believe that once you've gone through this, you've walked through each and every part of the code, you'll be able to understand and have a rough idea to build your first quantum correcting code. Thank you so much. If you have any questions, make sure you just send a message on Discord, or I'm sure there's people physically to be able to help out if you're stuck with the code. And another thing I'd like to mention is for the libraries, if you don't have some of the libraries here, because I already do, so I might not be able to detect some of the errors that some of you might have if you haven't had to run the libraries before. So just you make sure to add more and install them here and be able to walk through. Another thing I wanted to mention was this. If you're trying to draw and you're not able to use or to be able to see the circuit, how it looks like on this other side, you can just change it from MPL to text. And you'll be able to see the exact same thing, but in text form. And yes, that was the presentation. If you have any questions, feel free to let me know. And we can connect on LinkedIn and chat more about this. Thank you so much.
Yes, thank you, Muna. Thank you for a very nice presentation. So I have 2 announcements. First one, the last talk will be cancelled. So we will after this hand-on exercise, we have no longer a section. The day 2 is end, and the second one tomorrow we'll have a full day of industry companies talks and so on. So please bring on any people that you know who is interested in quantum, your neighbor and so on. You see, so please tomorrow we will have a IBM Quantum, Riverland, HiQ. Alice and Bob and also C12 welcome. And there are one company come from Singapore, like Anthropica Labs, that is our sponsor. And so that on. So please practice hand-on exercise. If you have any question, you can ask on Discord if you want to be sure that we will answer, or if not, you can ask on the team or ask the physical organizers. Thank you.
Bengali.
Ah, j'ai bien réfléchi. J'ai décidé. C'est par les ordres de comment. Je peux plus voir si la tâche est d'autres. Ça fait longtemps que ça fait longtemps que je teste. C'est la version 1. Ouais. Je suis plus à l'écart sur ce que
Vous savez, avec Armel.
Et là, j'ai re- pour les interprétations. Ouais. C'est la mission d'erreur pour l'équipe de charge. Et quand j'étais chez Winning, j'ai bossé sur le. Et là, et c'est vraiment difficile pour moi d'imaginer qu'on va parler d'ordinateurs quantiques qui vont être utiles sans avoir des gens qui sont capables de les programmer correctement. C'est quelque chose que je regarde en ce moment, je discute pas mal avec les gens de Unitary Foundation. Je connais Will.
Hi. One person's low issues.
Yes.
Yes, but the epoch channel.
Je demande si ça marche pas dans d'autres trucs. Hein. C'est pas.
No, I mean I am guilty. No, we are all remote.
Oh, okay,
So there is no office basically. It's a US-based company, but we also have a Ukrainian entity because like we have a large part of Ukraine, but we are all working remotely. So no, I mean yeah, my office is probably the office Paris, but
You working home on
yes, yes.
Okay.
Ah, écrit, hein, c'est bien.
I want to work in home.
No, okay. So right now we don't. We do have like sponsored in the UK. We are like, and also we are part of some European consortium, Marie Curie and this type of stuff. So it's not exactly CIF, but this happens. I don't know. So you would be.
I'm interested in a PhD. I mean, it's not still on that.
Yeah. But do you have like a topic in mind, or is it?
I am more interested in the patient areas. I'm also like in high performance computing, so I did how high performance for a computing has become.
Yeah, like because it's a specific way of working, infrastructure like this.
Yeah.
So.
I have a very much I have a photography and writing both my internship also in one night.
But so you will be looking to start, so you finished your master, or you finished already? Okay. I think because I don't know right now exactly because in some of these for example my career and stuff like this, you have like deadline to apply, and it's always a process. So basically maybe just add me on LinkedIn. I can and we already possible. Or just like you can send me a message, and I can see what's going on right now. Because I don't keep track of all the deadlines of this type of stuff, but also I know it's not the same thing, and it's like, probably less interesting. But we did it this year, and we probably do it next year. We had like a summer internship, I think like paid 3 months internship.
But is it? I guess it's mostly for masters too.
No, we had like first of all, a lot of PhDs applying, but we had a mix of. So we did take master students, but also in.
Yeah,
Okay, part time doing their PhD, or like even posing. That's not posing US, but posing their PhD and then starting after something like this. So that's totally fine. So if you're next summer, if you're just still looking for something, then that's totally. We'll probably do it again because we had like good experience, like good results, and working with nice people. So that's also. And yeah, just send me a message, and maybe if you have a quick, description of your like.
Of course.
Yeah, and I will look around, see if there are like deadlines or like that you can still work with. No problem.
Ouais, j'ai fait doctorat sur les langages de programmation. Je l'ai fait avec Sam State. Je l'ai fait, j'ai bossé sur les langages de type Wire, un peu sur Kuiper. À l'époque où les gens pensaient par contre qu'il fallait des langages de haut niveau. Ouais, 4 ans. Ah ouais, ça fait 10 ans que je suis dans le domaine.
Ah, ça fait 10 ans.
Ouais.
Du coup, pourquoi tu fais
Oui.
dans une conférence il y a 2-3 mois, c'était
C'était à Munich.
Munich, c'était un mois.
Okay.
Ah, je crois. C'est à Télécom.
Ah oui, j'ai fait une présentation à Télécom. Ouais, c'était TQCI.
Ouais. Et déjà.
Ouais, j'étais toujours à Wheeling.
Je te connais.
Ouais.
Après, j'étais.
Ouais, ça fait, c'est nouveau, c'est pas ça. Quand je voulais faire un peu un congé sabbat. Parce que moi, je préfère le logiciel libre. Il y a pas mal d'options si tu veux développer des logiciels libres tout seul, et indépendantes, que ce soit par la version Mozilla ou par la Vita Foundation.
Oui, oui, je voulais répondre au dernier top. Pas grave. Merci encore pour l'invitation. Je serai encore là demain. Ok. Pour la table ronde. Oui, la table ronde. C'est l'après-midi. J'ai eu l'après-midi. Donc je pense que je viendrai. J'ai des trucs début de matinée. Oui.
Super.
Ouais. Ah, du coup, c'est sur votre projet là.
Non, du coup, bah là, on est en train de.
Ah, d'accord.
C'est juste un peu.
Ah, ok.
Demander qui.
Ah, oui, ah ouais.
Et du coup, pendant les débuts d'année, on était tout le temps en train de. Ouais, mais il manque cette option. Oui, bon, surtout moi. Autant c'était plus bien. Bah, moi, je m'occupais de coder en fait les parties de MyQLM qui n'existent juste pas
Ah,
et qui ne permettent pas de simuler du bruit, qui ne permettent pas de. Du coup, j'arrêtais pas de me plaindre. Et du coup, la semaine dernière, en fait, c'est lui qui avait codé. Voilà. Du coup, dommage, parce qu'on a pas prendre.
Qu'est-ce qui s'est envie?
Bah, en tout cas, j'ai l'impression. Je sais pas, parce que pour l'instant, je sais pas, parce que pour l'instant, c'est vrai que c'est de trucs qu'on ne pouvait pas faire avec MyQLM pour l'instant. Et après, on est dans un niveau débutant. Là.
C'est ça la fin.
Bah, je veux dire, là, on est en train de tout faire à la main. Et ça aussi, avec MyQLM, tu peux définir un circuit à la main et faire des trucs dessus.
Comme mesure stabiliseur, tu vas rajouter un qubit.
Bah, là, en fait, pour mesurer un stabiliseur, je sais pas, en fait, je pense pas comment. Je sais pas, mais je sais pas s'il existe des outils qui donnent le stabiliseur et ils mesurent, effectuent la routine de créer le circuit. Mais ça, de toute façon, je crois qu'on va pas le voir au cours de la. J'ai tout cassé, c'est fini, c'est boum, c'est perdu, cassé, détruit.
Right. I might have to leave at some point in like the afternoon. I'm not quite sure. Same thing on the Thursday as well. Because I can't isolate all my work. But it is.
Are you from it's not it's great. From which company?
I'm from a university. I'm from the University of Vienna. I'm a postdoc. I want to go into the private sector. And the thing is, my work has connections to exactly those quantum LDPC codes. Or well, generally to error correction.
So you work on
A little bit. Strictly speaking, I'm a geometer. I do geometry, I do cube complexes, graphs, negatively curved manifolds, like that. But it turned like, you know, surface code, like what's the surface? You cubulate a negatively curved surface there usually. And there is a version where they try to do it with a 4-dimensional hyperbolic manifold.
Oh.
All that stuff is right in my backyard. And same for LDPC codes. If you want them to be nice, you need the cube complexes and nice geometric properties. And it's literally the geometric properties that give you the good, like the good overhead, the fast decoding, and so on. Which is why, okay, there's a chance.
I understand that this can be very thrilling to work in that when you understand.
Yeah. Especially because like you don't usually do those things because you care about quantum computing.
Yes,
right?
you do just because it's fun.
Yeah, yeah, or like there are other there's many questions that lead you to these objects. But it turns out like it's the thing about math, right? If you develop the language for math to describe one thing, you also develop the language to describe many other things. But then you have to find those. So yeah. I guess yeah, tomorrow, probably the morning, probably the afternoon.
Ok, good. Je sens qu'on est les trois seuls à être en prix de. Ah oui, c'est vrai, ça continue où après? Je crois que c'est la dernière. Ah oui, non, c'est vrai. Il y a Ah, ok. Donc là, il y a juste un hands-on practice, avec personne, hands-on practice tout seul. En même temps, c'est vrai, pourquoi pas. C'est plein ou quoi? Ah, c'est plein, oui, c'est plein. Du coup, merci beaucoup d'organiser. Avec plaisir. Avec plaisir. Je pense que c'est plus utile en envoyant un message sur le groupe Info du 24 en disant bah, venez même si vous n'êtes pas inscrit. Ah non, il faut que vous venir. Hein, ouais, je sais. Mais ça sera IBM et C12. C'était directement le café, pas le fil dedans. Et je me dis. À partir du framework en 30 à la table ronde. Barriers in front of life. Du coup, mais c'est de 13h30 à 14h30 et du coup après. Ça sera une présentation de IBM. Ouais. Ça sera après un talk de Alexandre. Du coup, la partie qui est dédiée au recrutement, en gros, la manière dont je vais leur présenter, parce que moi je peux très bien leur dire, bah, juste venez parce que c'est super intéressant. Le problème c'est qu'il y a certaines personnes qui sont plus intéressées. Ah. Bah, écoutez, je vais juste prévenir qu'on n'a pas besoin d'être inscrit. Non, c'est une blague. On n'est pas tous comme ça, je précise. Hein. Et du coup, ça sera demain, il y aura des pizzas. Sponsorisées par IBM. Sérieusement? Ouais, ça on n'a pas annoncé, mais. Ok, bah je crois qu'on va pas annoncer, sinon je ne me rappelle plus. Du coup, apparemment, il y a des. Mais attendez, ah, mais ça c'est pratique parce que vu que nous, du coup, ça on peut venir un peu plus tôt et manger sur place. Je crois que ce sera après la table ronde, ça sera à la fin. Ok. Ah non, mais la question c'est est-ce que du coup on mange au Magnon ou on vient. C'est quoi le nom? Il vient de dire qu'il y avait des pizzas de IBM. Ouais. Ah ouais, les pizzas de IBM. Du coup, ne le dis pas. Non, mais je vais pas le dire. Moi, je vais dire réunissant plein de startups. Voilà. Tu peux mettre la carotte, c'est pas. Non. Non, je pense pas. Non, mais juste, j'ai. Déjà, après, les gens ne viendront pas ici juste pour. Oui, voilà, les gens ne viendront pas juste pour les pizzas, ça c'est sûr. La distance déjà. Non, tu veux dire. Oui, c'est ça, le fait que ce soit long. Deux doctorants. Non, parce que, écoute, premièrement, parce que tout ce que j'ai programmé, je l'ai fait sur MyQLM et que ça marche. Et deuxièmement, parce que, attends, là pour l'instant, on a juste vu que, ok, il y a les mêmes options. C'est peut-être un peu plus clair au niveau de comment est-ce que, dire, la manipulation de registres de bits classiques, etc. Mais, écoute, demain, il faut que je fasse, du coup, que je mette au propre ce qu'on a fait. Il faut aussi que ce serait bien aussi de regarder si Qiskit offre des options pour le calcul de code pour l'évaluation de stabiliseurs sur son clip. Parce que c'est surtout ça qui nous ferait gagner du temps. Ah oui, et aussi s'il dispose d'un émulateur de processeur bruité. Ça aussi, ce serait cool. La seule raison qu'il pourrait nous faire passer sur si jamais il possède nativement un émulateur de processeur bruité, et également à quel point est-ce qu'on peut contrôler les modèles de bruit. Je crois que Qiskit, il y a un qui s'appelle c'est un émulateur avec les mains. C'est un backend bruit. Il contient des gates. Avec les mains, il y a, je crois, Vanilla, fake Vanilla, je crois. Et justement, moi, ce que je me demande, c'est à quel point est-ce qu'on peut contrôler ça, parce que nous, ce qu'on aimerait, c'est ensuite vraiment voir comment est-ce que le modèle d'erreur, il va influer sur l'efficacité ou pas du code.
Ah, ok.
Et donc, étant donné que, comme c'est développé par IBM,
S'il y a ça, il y aura moyen de...
ouais, mais ce que je me dis, c'est que, en revanche, IBM, eux, ils travaillent sur des qubits à transmon.
Ouais, t'as quand même un modèle d'erreur. C'est pas aussi
Ouais, voilà,
biaisé, mais
en gros,
genre,
faut voir,
c'est des constellations qui en prennent compte.
faut voir, est-ce qu'on peut leur dire, bah, je te donne ce modèle d'erreur qui est complètement biaisé.
Après, tu peux faire ça en tout cas pour les ports, faire avec les IRF qu'on peut mettre une méthode d'erreur sur les portes, enfin, pas sur le, pas en tant que contenu, mais sur les portes.
Oui, avec MyQLM, on
Oui.
peut faire ça.
Oui.
La question, c'est est-ce qu'ils ont un truc qui nativement te fait ça? Alors. Paris. Pas besoin de s'être inscrit. Même si c'est mieux. Même si c'est mieux, les inscriptions sont encore ouvertes.
On n'a pas besoin de ça.
Ok, ouais, je vais pas mettre trop de mots. Pas besoin de s'être inscrit. Je vous envoie le programme. Vous verrez, c'est passionnant.
R. Et
Ah, ouais.
Logistic with models.
Hmm.
With interfaces. C'est with models.
C'est un backend.
Ouais.
Le backend, tu peux le faire en modèle de maille. Par exemple, le métrique.
Par exemple, ok.
Et c'est effectivement ce qu'on veut faire de toute façon. Sur MyQLM, pour l'instant, ce qu'on essaye de faire, bah, c'est de ne pas avoir à gérer manuellement le bruit et de juste créer une classe. Du coup, faire des classes en Python. Je me suis rendu compte que c'était pas cool. Du coup, j'ai fait une classe QPU Noisy où tu lui donnes un modèle d'erreur, mais pour l'instant, c'est que des erreurs qui s'appliquent lorsqu'on met une porte.
Et quel genre d'erreur que vous avez injecté
Alors, pour l'instant, là, on est encore essayé de faire que tout marche, mais l'idée, ce serait de, de voir des erreurs qui peuvent apparaître en fonction de la technologie. Donc, par exemple, les pertes de boutons, ce serait des erreurs non unitaires, par exemple. Et des erreurs de phase aussi, et qui pourraient dépendre, par exemple, de la porte.
Ouais, c'est une porte qui est logique et qui n'est pas d'erreur. Entrer par un, sortir par un, c'est pas. Après, tu rajoutes le modèle de noise après la porte.
Ouais, c'est ça. Là, ce serait bien de prendre aussi en compte le fait que au cours du temps, on a une cohérence des qubits. Le problème, c'est que faire ça sur émulateur, du coup, il faut savoir combien de temps ça prend de faire.
Ça, je pense que dans
ouais, non, mais du coup, même.
Dans l'article que j'ai, je t'ai un peu détaillé là-dessus, je pense.
Mais du coup, ce que je veux dire, c'est que même quand tu n'appliques pas de porte, les qubits qui sont en attente, il faut aussi prendre en compte. Du coup, on peut dire que tu appliques une porte identité.
Juste, tu considères que, que tu as des portes et que le temps s'écoule le reste.
C'est vrai, tu peux faire ça.
Oui, donc je pense dans le premier temps, on n'est pas d'aller. On aura des trucs corrects.
Aïe, aïe, aïe. Ouais, je suis en train de faire un message.
Hello guys.
Non, il n'y a personne.
Ça va rester une demi-heure, je pense que.
Aïe. Non, ils sont tous partis. Tu peux arrêter depuis là. Et comment pour relancer après?